Going live, and then we're live. Okay, hello everyone, and welcome once again to the Latin American Webinars on Physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. Today we're having webinar 174 with Jaime Hoefken as a speaker, who is a postdoc at the National Center for Nuclear Research in Poland, NCBJ. Jaime actually started his physics career here in Peru at the PUCP, and then continued with a PhD at the Universidad di Bologna. He finished the PhD last year and has just recently moved to Poland. On a personal note, I have known Jaime for a very long time, very long time. So I am thrilled of having him here today, giving his presentation. Today, Jaime will talk about mechanisms for dark matter capture in white dwarfs. And well, before we begin, as usual, let me remind all viewers that you can ask questions and make comments via the YouTube live chat system. Moreover, we're also aware that the KM3Net collaboration will release some results later today. So we have agreed to finish this presentation just in time so that whoever is interested can also watch that presentation too. So, okay, let's get on with it. Jaime, we're all yours.
Hello, good morning or afternoon to everyone. Thank you for the invitation, Joel. It's nice to be here sharing with you one of my last projects. So I'll share my screen. Okay. Okay, and this needs to... Okay, no. Well, so I'm going to talk about dark matter interactions in the white dwarfs. The main motivation is to study how dark matter can be captured in white dwarfs. You can see the paper is in this number of archive, and I worked this with Maura Ramirez and Shiwan Hor, two collaborators. So I'll be fast so we can finish on time, but there are some points that might not be completely covered because it's a very complex topic. So let's start with the motivation about this, about capture rate. What is that? So we know that the standard model of particle physics, it's a very successful theory, but there are still some topics that cannot be explained, such as this dominant matter component in the universe. We call it dark matter, if it's matter. The baryon asymmetries of the universe, gravitational interactions at a quantum level, and even neutrino oscillations are not accounted from the standard model. And well, dark matter is one of these topics that we still don't know. Why dark matter? Because first we observe the galaxy rotation curves, and we see that the velocities cannot be accounted for just by considering Newton laws and maybe GR, general relativity, and the disk we observe of matter. We see that the velocities would imply, if general relativity is okay, that there is more matter that we cannot observe. That's what we call dark matter. We also see some gravitational lensing, so bending of light because of matter in the middle, let's say, and we observe that matter. The matter we observe cannot account for all these observations of gravitational lensing. There should be more matter that we cannot see. Also, the CMB spectrum, this cosmic microwave background, there's some differences in temperature in it, and we cannot account for that just with the matter we observe. This is actually the strongest reason now. Also, there are people working in large-scale structure formation of the galaxies that they claim that we need this dark matter to produce the galaxies as we see. So dark matter is a topic. It's a hot topic now. We are still looking for something. Some people look for particles, some other people of some structures of matter. Some other people look for deviations or changes in the equations of motion. That's actually harder to account for, but we still don't know. We can go even beyond just dark matter and say, okay, there might be new physics, new particles, new particle physics beyond the standard model that we cannot see directly. But that can account not just for the dark matter problem, but also for some anomalies in experiments. This is, for example, a model I worked on in the last papers I've written. And some of these models, they claim you can be connected to the standard model through portals, which are particles, scalars, vectors, or maybe through neutrino mixing. So all of these dark extensions of the standard model and dark matter are particles that are out there, and we want to detect them. We want to understand how they are if we can ever observe them. Okay, so experiments for dark matter, we want to observe dark matter. There are many ways. One way is the direct detection. So this is from down to up. So we have a dark matter particle that interacts with a standard model, and then in this case we would have an elastic collision, and then there's something that happens to the standard model particles, and then we observe, okay, there's something hitting my atoms. So for example, in xenon experiment. Other experiments are indirect detection. So you have dark matter particles that, for example, annihilate, and they produce standard model particles that we can observe, and we cannot account for that flux. So we say, okay, maybe there's something producing this. This is the indirect detection. For example, in IceCube, they've done searches for dark matter in this way. And third, colliders. It's from right to left. So when dark matter, when standard model particles annihilate or interact, they can produce in these high energies particles that are not observed, that we can tell the difference with neutrinos because of lepton number conservation. And okay, in the end, we could say there might be dark matter here. For example, Atlas, the LHC. But okay, but together with those methods, we could have a new way of detecting dark matter directly. We could use a star as a huge detector. That's the point. And this has a long story, but in this case, I will work with compact objects, and particularly with white dwarfs. Let's see how we can do this. White dwarfs. So to understand what a white dwarf is, we have to take into account how the life of a star ends. If the star is really small, from 13 to 80 masses of Jupiter, then it's called a brown dwarf. It cannot really burn all its material as a normal star, and it just stays the way it is. It's called a brown dwarf. But if it can burn the materials it has inside, then the end of its life can be what we call a white dwarf, which is if the original star is from 0.17 to 1.33 solar masses, then what happens is the star starts collapsing after burning all. So if it doesn't have this nuclear fuel burning, there's no pressure coming from those interactions, and then the star starts collapsing towards the center because of gravity. So electrons, they start to accumulate in this small volume with respect to the first star. And so we start having this degenerate pressure because electrons are fermions, and they cannot be, there's this Pauli blocking, they cannot be in the same state. So they start going to higher levels of energy. And this produces a pressure that for these masses, it can stop the collapsing of the star. And what we have, this electron degenerate star, is called a white dwarf. Then if the mass of this collapsing star is greater, then we have a neutron star. So what happens is that this electron pressure cannot stop the collapse. And so the matter starts becoming more and more dense. And at some point, this degeneracy even of electrons, of protons and neutrons, then there's what we call a neutron drip. Well, you start producing free neutrons because they cannot decay. Basically, they cannot decay because to produce an electron, when neutron decays, it produces an electron. So you would need so much energy to produce this electron because of the Pauli blocking, that then the neutrons start being free. And these free neutrons can also be degenerate and can also generate a pressure which is much stronger than that of electrons. And so we have a neutron star. We don't really know what happens inside the neutron star. I was doing a computation for having a profile of a neutron star, and I was searching a bit about this topic, and I found that like 350 equations of state for the neutron star. So we don't really know what happens inside, but we can have an idea, of course. And then if the mass we have is even larger, then gravity wins, and we have a black hole. Everything collapses, and well, we don't know what happens at the level of particle physics inside the black hole. Still don't know, but it's supposed to collapse to an infinitely small point. But okay, whatever happens, we don't know, and we have a black hole. So these three kinds of objects here, not the brown dwarf, are called compact objects. Let's say they are very dense. I don't know if the word dense applies to a black hole, but yeah, there is so much matter inside a small volume. So characteristics of white dwarf, their density goes from 10 to the 9 to 10 to the 6 to 10 to the 9 kilograms per meter cube, mainly composed of carbon and oxygen. The forces we have, the gravitational force, the degenerate pressure of electrons, and Coulomb forces also. The mass, it has to be less than 1.4. It's called the Chandrasekhar limit. And the equation of state, so the way we compute things is using the equation of state of the relation between energy and pressure of the matter inside. That's for a white dwarf, one usual equation is called Salpeter, and the Tov equations. I'm going to show you the Tolman, Oppenheimer, Volkov equations that are basically general relativity equations for matter, not for vacuum, but for matter in a kind of Schwarzschild metric. So, capture of dark matter by stars. In these compact objects, especially, I'm going to talk about the white dwarfs. So we can capture dark matter, and this has a story. It actually started with Spergel and Press, this paper from the '85. They were trying to account for the solar neutrino problem. It's quite interesting because they were not thinking of capturing dark matter as such. They were thinking that if you capture these cosmions, these solar cosmions, these WIMPs, as they called them, then you would change the transport equation in the sun, and then you would explain the solar neutrino problem. Many of you I know have worked in neutrinos, and this was a long-standing problem until we explained it with, but not exactly neutrino oscillations, because but at least with this effect of matter and neutrino matter states in the sun. But they were trying to explain that through these capture mechanisms. Right after they published their paper, Faulkner and Gilliland, they had already computed this capture rate of dark matter inside the sun. But they didn't publish. They did it, like, they had done it 7 years before, but they never published it. They thought it was a bad idea. And then when they saw a Spergel and Press paper, okay, they published. But then there was another very interesting thing. which is this paper by, oh, sorry, I'm trying to disappear. This, hide, okay. Want to hide this. Okay, no. So this Geiser et al. From the 86, they started studying this capture rate as a capture of dark matter to detect and see dark matter. So there are these two motivations, trying to explain the solar neutrino problem and capture of dark matter itself. And in the 87, this good paper, and he explained that he studied this capture by Earth and the Sun. And this is a very important paper because most of the equations we still use today come from this paper. Okay, let's go on. So what happens? What can we measure with this? We study a star, we see that the star can capture and accumulate dark matter inside. And you could study how much mass you accumulate or how many particles you accumulate. And then you can see if there's some effect in gravitational effects. We have seen that these gravitational effects are very small. Or emission of particles if dark matter is can annihilate, and then you can have a flux of something else, maybe neutrinos coming out from the star. And the other thing you can measure is how you heat the star. So instead of measuring how many particles you capture, you can measure how much kinetic energy you are depositing in the star. And that kinetic energy translates into heating, especially of cold stars. There are these two paths we can take for this. So, and what happens is that we have a dark matter particle with a speed far from the star, then gravitational force and any flux, it creates a flux that accelerates towards the star. Then this reaches with a particular new velocity. I've called here W would be the velocity on any point inside the star. It depends on the position with respect to the center of the star, of course. And then it scatters and goes out. And if this velocity of going out, this V I've put here, is less than the escape velocity, the star, it gets trapped. That's the whole mechanism. So what we measure is the interaction rate, which is the probability over time. And this is computed by this ratio from 0 to the velocity of the escape for a particular point of the star. And this R is defined, of course, is proportional to the differential cross-section. So the idea is, okay, I computed the differential, I compute the cross-section each point just in the parameter space that produces outgoing dark matter particles that will be trapped, captured. And that's basically the mechanism for computing how many particles will stay in the star. So the formula obtained by well, in this case, this is by us actually, but the first one is, as you can see, is in the lab frame. People usually work in you will see expressions that are a bit different from this because they work in the center of mass frame. We prefer to work in the lab frame. So we have basically the cross section and some other parameters that account to transform that to a probability and to include the flux. And then you usually define the capture rate like this with a Maxwell-Boltzmann distribution of velocities of dark matter. But in our case, we wanted to study the effect of a particular velocity. So what happens if let's say the energy, which is related to this velocity far from the star, if the energy of the dark matter is whatever energy we want to consider. So even to high energies, there are many studies focusing on boosted dark matter, for example. So we wanted to see how's the effect for a particular velocity, and maybe which velocities could be visible for the star. So that's why we changed this distribution with a Dirac delta for a particular velocity. Then we integrate over the whole star. And we took out this, this is the density of dark matter around the star. So basically, we're not accounting for the fluxes. We're just accounting for the effect for a particular velocity. And we call this the capture density rate. Okay, so this is supposed to be a tool for people working on capture rate, rather than a definite answer about how much capture there is, because you need to consider the fluxes, of course. So this is model independent with respect to the fluxes. Sometimes it's important to consider how opaque the star is, because if the probability of capturing the dark matter particles starts to be close to 1, then the problem is that the flux will change as it goes through the star. So, but we will work in what we call the optically thin limit, in which the probability of getting captured is low enough not to need to account for the opaqueness of the star. And the limit is given by this geometric capture, which is the capture rate for when you have this probability 1 of being captured. So everything is captured on the surface of the star. And so this is just a way of knowing if we are in the optically thin limit. We need to be far from this limit. So I think that in this study we produced, the most interesting things is how we modeled the interactions. And this was a long study, and I hope to explain it at least briefly. So we considered first 2 kinds of interactions. We consider this dark matter as fermions. That's the first thing. We have fermions, and they interact with standard model matter through a dark photon in one case, or through a scalar. Okay, we consider these 2 cases. They are inspired in many models that exhibit these kinds of interactions. And well, these are the diagrams, so you have an idea of the interactions we have. So this dark photon, for example, it can interact with electromagnetic currents, and the coupling is not just the electromagnetic charge, but multiplied by this kinetic mixing parameter called epsilon. And it can also interact with the dark matter currents. And this GD would be that dark coupling that can be high, because it's just a coupling of the dark sector. In the case of the scalar, we have almost the same, but now the interaction with the dark matter currents would be the same. But with this is about like Yukawa couplings. And then with the standard model particles, we considered that the I and J they need to be the same. So you can have one particle here and then the scalar connecting both. So these are the interactions we considered. We haven't considered them at the same time. So or the vector interaction or scalar. And then what can happen? What interactions can take place? We have considered with respect to different energy ranges. If the energy is low, then the dark matter particle can see the whole nucleus and interact with it coherently. So what we'll consider carbon nuclei. And then this is the kind of interaction we could have where N would be a nucleus. When it has more energy, then it can start looking at the nucleons inside the nucleus. So in this case, the diagram looks the same, but in this case, this N would be nucleons. If we go to very high energies, then the dark matter particle can see the quarks inside the nucleus. We have what we call DIS, the deep inelastic scattering. So in this case, you produce many things. From here, you can have jets. You can study these jets or monojets that are produced. And we can follow the Parton approach to do the computations of the cross-section. And the novelty here is that we considered a process for not so energetic interactions such as DIS, but inelastic interactions where this can happen. So the dark particle interacts with a nucleon. This nucleon gets excited to a resonant to a resonance. It's an N resonance or delta resonance. I'll talk about that later. And then this resonance decays into another nucleon and a pion. This is quite interesting, not just because of capture rate, but also because we can study these processes, these cross-sections in experiments and see if this new physics can produce this nucleon and pion, which is really easy to detect and to see in detectors. Okay. So, interactions with nuclei. There are many ways in which we can try to model an interaction with a whole nucleus. We considered two approaches, the non-relativistic and the Fermi-symmetrized Wood-Saxon approaches. Let's start with a non-relativistic approach. So this has been used by xenon experiment, and many people working in dark matter at low energies, they use this. Basically, what you do is you take the interaction term, the Hamiltonian, and then you look for a Galilean invariant expression. So you consider it to be non-relativistic because of the low energies. And you extract some parameters that are, let's say, relevant in this Galilean invariant frame. And so we have, for example, the relative velocity between the dark matter and the nucleus. We can also have the three momentum, transfer momentum, the three momentum. We're not working with four vectors. And then we build with these quantum operators, including the spins, as you can see here. This is the part of the velocity normal to q. So we're using these five non-relativistic operators, and we treat them as, let's say, classical quantum physics. And we create these states where we have the momentum and angular momentum of the dark matter particle and the nucleus, and also the nucleus inside the nucleus, actually. So I'm not going to go deep here because it can be complicated and we don't have time, but mainly people have studied different possibilities, different operators that can arise from these constructions. And they have performed a study to see how we can build first a Hamiltonian with these operators, and then with these Hamiltonians, how we can compute the transition probability for this interaction. And what is used and considered here is the nuclear shell model. So they consider how nucleons get excited in the nucleus. Nucleons in the nucleus, no. So that's the nuclear shell model. And well, these are the results by papers that have studied this model, this non-relativistic model, and all the citations are in the end, by the way. I can send you the presentation. And then we can apply this to our case. But to apply it, we need to construct the operators from our model. We basically expand the bispinors by considering that the momentum is small with respect to the mass. And this is what you obtain when you expand them, so that for the case of the dark photon, this high energy interaction term becomes this one here that you can see, basically. And then the same for the scalar. We can also build, and it's a very simple one, just with the first operator of those that I showed you before. The only thing is that we need to account for the coupling between the scalar and the nucleus, and the nucleus, sorry, the nucleus. And to do that, you need to consider the effect of gluons. And okay, I'm also showing you a source where you can see how to compute this. But this is how you compute it. These numbers are all in the paper. You can, if you read the paper, you'll see the specific expressions for this. So here we're accounting for an interaction at low energies. If we go to a bit higher energies, not so high, but a bit higher, then we can use this Fermi symmetrized with Saxon approach. It is basically what they do. They use, well, it started with Helm, actually, Richard Helm. This is the paper. So you consider that the form factor, it takes you from an interaction with a point particle to an interaction with a system. In this case, the nucleus. And it's just the Fourier transform on the density of the particle, this complex particle they're considering, in our case, the nucleus. So the Fermi symmetrized with Saxon models this form factor in this way. You can see here, where all the parameters are related to a model, a volume model of the nucleus, which comes from Wood-Saxon and with a correction by Fermi. So we use this approach. There are other approaches. I'm just quoting them here, but this was I would say, the most efficient one to do the computations. Actually, we obtain exactly the same by using Helm. And so here you can see it's a paper taken from here. And you can see the differences in the form factors. They are really close. The blue one is the dipole, just the dipole one. So, okay, of course, it doesn't work. The other ones are better, and they're very close, as you can see. So basically, the expression we have, I'm putting here the scalar one, which is the simplest. This would be the differential cross-section by taking a point particle and then multiplying by the form factor. And this is the final solution for the total cross-section. Okay. Interactions with nucleons. In this case, I'm not going to go deep. Maybe I will be fast, because basically what we do here is we took the form factors of the standard model for interactions with nucleons, and we just renormalized them, let's say, with respect to the couplings we were considering. So basically, we would have that the interactions take the following form. These are the form factors. These ones, the FIP, FIN, all of them are from the standard model. And then we can construct them also using the dipole function and the Sachs electric and magnetic form factors. They come from electromagnetic interactions. And then we can construct the amplitude just by plugging in those form factors. Okay. For more information, you can go to the paper. And then in the case of the scalar, it was a bit more complicated, because we had to translate vectorial form factors to scalar ones. I'm not going into this because of time, but you can go to the paper and discover how we did it. So interaction through resonances. So in this case, we basically have, well, there's a whole story of how this was built. I'm going to the main elements. Feynman, Kisslinger, and Ramdal, the 71, they were studying a relativistic quark model to account for interactions, transitions from different hadrons, especially baryons. Because resonances or baryons are excited states of up and down quarks. In our case, just up and down quarks. We didn't consider strange ones, but okay, they can be accounted for using this model. And then Ryan and Segel in the 81, they computed the cross sections for neutrinos upscattering to a lepton or neutrino in the neutral current, producing these resonances and then decaying into nucleon and pions. And this model was very interesting. It is used actually by Gini to compute resonances. Then this was corrected by Berger and Segel, the 2007, by accounting for the mass of the lepton. And then last year, we did the next step, which was, okay, let's consider dark matter. So you have two elements with masses. And then you also have a propagator that might not be just 1 over the mass squared, which is what they use for the weak interactions. Of course, the masses are really high. Here, not necessarily. So basically, the recipe, short version of the recipe is that you take this part of the diagram, and this matrix element is considered as a vector that interacts with this current, with this transition. And you use this vector to account for the different changes in helicity. You have four possibilities, because you can have here 2 helicities for the incoming chi, for the outgoing chi, 2 helicities, so four different combinations. And then those generate different transitions. And what we do is we consider all possible transitions. The transitions are here. Well, depending if this resonance is a delta resonance, so spin 3/2, or an N resonance 1/2, you have all these possible transitions. Each of them has to be treated separately. And using the Feynman-Kieslinger-Randall model, you can compute these form factors. Then you sum over all possible resonances. Some of them interfere, some of them not. And you compute cross-section by considering that the resonance has you consider a Breit-Wigner factor, which accounts for the fact that it's a finite width, so it decays. It's produced nearly on shell and then decays. These are the possible processes we can have. The p proton and neutron, and all mediators are neutral. This is, for example, the prediction of Ryan-Segel for this process to a delta plus, and you can see that the model is quite good. And after working with the transition amplitudes, from here we will have the form factors. Then we compute the differential cross-section for different kinds of transitions. As I told you, lambda 1 and lambda 2 account for the helicities of the dark matter, ingoing and outgoing. And then you can do the same for the scalar. And finally, you just integrate everything and you have the total cross-section. In case of DIS, this is a more well-known approach. You take the partonic approach, where each quark or parton takes a fraction psi of the momentum of the nucleon. And then, well, you use the Bjorken scaling variables and elasticity to compute the interaction with every possible parton. You have not just 3 quarks, you have many partons inside the nucleon with respect to the energy. It depends. And then you sum over all distributions of quarks inside the nucleon. So this is a very well-known result. I'm considering also the masses. Usually, if you see the literature, you don't see these terms. Some terms are different because I'm considering that this mass can be high of the dark matter. And this is for the scalar. So we started some benchmark for the capture rates. Going back to the capture rates, these are the benchmarks. So we have a light and heavy mediator for the vector case, and just a heavy mediator for the scalar, because the light mediator wasn't really different. So for the light vector, these are the cross sections, the total cross sections. As you can see, these are for the nuclei. So depending on the model, you have really different results. But then for some energy, they start to be close. This, which is the non-relativistic, goes up because it cannot account for higher energies. But then you can use both to model. Of course, for the lower energies, you use the non-relativistic. For higher energies, the Fermi-symmetrized Wood-Saxon. This is the resonance. We chose this case because the resonance cross-section is higher than DIS. It's interesting to see that. For the heavy vector, DIS is more important here. As you can see, the nucleon one is a red, by the way. And then for the scalar, we can see that the resonance is not important. Also, DIS is very low. So here, mainly you have low energies. So our results, the capture rate density, how much you can capture. These are the plots. As you can see, lower energies are really high in capture with respect to, we want to compare this, by the way. These numbers cannot tell us anything without fluxes. So we can just compare. These numbers are 8, or with respect to this, it's like 6 orders of difference with respect to this interaction with low energies. But this is still interesting that this is not 0. And then if we have a high flux at higher energies, which because of the speeds can get really high with respect to the lower energies, then this could be visible. The next step would be to compute with realistic computations of fluxes. So this could in principle be visible. If we go to higher mediators, yeah, well, in this case, this starts to be, in general, low, but everything is lower. And then the orders are not so different, actually. Are different, but not that much. So here we could also see the effect of this. And for the scalar, here the differences are more dramatic. It's harder to observe the higher energy capture rates, so capture of particles with higher energy. It makes sense, right? Because higher energy is harder to stop. But in general, in these 3 results, something quite interesting is that there is a gap with no capture. And this is because in elastic interactions, there is a very strong bound on the parameter space. And then if the velocities that can be captured are out of this parameter space, you have no capture. Then you go to inelastic, you have more freedom, because then you have more things, more ingredients, so the parameter space is wider, and then you can capture. Especially with DIS, in which you produce so many things that you take more energy from the dark matter incoming and outgoing. So conclusions, I leave you with the conclusions because it's 4 minutes more than I thought. So I leave you with the conclusions, and well, we can have questions now. Thank you very much.
Super. Thank you very much, Jaime, for the very nice talk. So let's get on with it. Questions. I am aware that Nicolas has a question.
I have few. Can you hear me?
Yes, of course I can.
So thanks, Jaime. Super nice talk, very clear. I have several questions, many.
Please.
Will you please go back to your slide 21 first?
Yes.
Please. I think it was 21.
How did you count them? Okay, yeah, the numbers.
Well, you have numbers.
Yeah. Not in all. I don't know why. Okay.
So it's when you present, I think, what the capture rate?
Here or here? This should be.
No, it was not. Yes, previous one.
This?
No, when you have, I think, what the capture rate and you have the Maxwell-Boltzmann
Yeah, okay,
distribution.
here. Yeah.
Yes, that one exactly. And then you change it to the delta. So
Yes.
first, why a Maxwell-Boltzmann?
Okay, Maxwell-Boltzmann is a distribution considered for dark matter in halos.
Yeah, but you expect wait. But that's the distribution in the halo or inside the white dwarf?
No, in the halo. The ones that are around the white dwarf, let's say.
Okay.
They're
Yes.
usually modeled with
I completely
Maxwell-Boltzmann.
Okay.
Yes.
Okay. Then that's in principle what you have to use, I understand. But then you say that you trade that for a delta.
Yes, because
It's,
I'm
it's
not
just an
studying.
approximation.
No, I'm not studying the capture rate of a particular arrangement of dark matter. I'm trying to see what's the sensitivity of the capture rate with respect to specific velocity. So I
Okay,
change
and
my
then you're doing
distribution to
that
specific
for
so I can
all the
compare.
velocities.
Yeah, so I can compare.
Okay.
That's why
Okay.
I work with the capture rate density and not the capture rate.
I see. Okay.
It's like a map. We want to see a map, how much you can capture for different energies. So we can compare low energies to high energies and yeah.
Okay, thanks. And related to the captures, did you study or did you consider the effect of dark matter self-interactions?
No.
But that could be principle done, right?
Yes, of course, but that would be a next step. So the self-interactions are important for two things. Annihilation, and then you can study a flux coming from the star. Or also in evaporation rates, which is exactly the same. So in evaporation rates, you need to consider that. We haven't
But also
considered that
capture, you
because
can have like self-capture, I
self-capture
imagine.
inside. You
I
mean,
mean,
okay,
elastic interactions of standard
with the dark matter
of
itself.
dark matter. Yeah.
Yeah. No, we haven't considered the effect of already captured dark matter with dark matter.
Okay, good, thanks.
Yeah, because you know something, if you want to put limits with the mass, so how much mass you can deposit, okay, those limits are far beyond of something observable inside the star. So you cannot capture that much mass. So I would say that the self-interactions for capture would give you an order, a negligible order of capture, because you don't have much. I haven't worked on that. I've just seen the results of people studying that. So that's why people look into annihilating and producing some fluxes or heating.
Okay, thanks.
Yeah, thank you for the questions.
Super. So we're really running out of time, but let's I'll send a question from the audience that's coming from the YouTube, from Jonathan Vignati. So do the low energy approaches consider effective theories of the high energy regime you consider?
Yes, that's exactly what I did. Yeah. So here, you can go to the paper if you want to see this more closely. You can go to the paper Marco Cirelli. It's cited by me in the end of the presentation. I can send you, so Joel can share. Can you share with people, or
we can put it as comments on the
okay,
YouTube video.
So mainly you take because you take this high energy, let's say, element, and then you build an effective theory by computing this. You really compute this element by element, like you open the bispinors using this approach. This is and so you use this to go from this high energy to the effective low energy. And I've put here the operators you have, actually. So all of these are operators worked by people working in this theory. Yes, and okay, I can show you briefly the Okay, non-relativistic. This paper, Cirelli, De Nobile, Panci, Paolo Panci, in one of the appendices, they explain how to do this. So if you want to have a closer look, you can go there.
Fantastic.
Mhm.
Great. Thanks very much for that. I don't know if there's any other questions from the audience. Nicolas has
I have
unmuted.
more questions.
He's got
Mhm.
another. Okay, let's go.
When you present the non-relativistic approach with this set of operators, if I
Mhm.
understand correctly, what you did is you took your model with a Z prime or with a scalar mediator,
Yes.
and then you compute like the Wilson coefficient of these operators. Is what you did? So you use this operator as a basis
No, it's
for.
not. It's not really the Wilson coefficients. What you do is, sorry.
I think it was a 32.
Wow, you really know the numbers. Okay, so you build this. So as you can see, I'm just expanding this and I obtain this expression. And these coefficients, these would be the coefficients I have, are the coefficients of these operators here. Only some of them appear, as you can see. And the second one doesn't appear. I don't know why the first authors that did this, they claimed, okay, there's a second operator. Okay, it's too small. We won't consider it. And then you go from the first to the third. But okay, that's tradition. I'm following tradition. And then you just build things. So you build this, and then your coefficients will come from the coefficients that multiply your operators that are here. As you can see, they would be different for the neutron and for the proton. And then that's all you need to do. For the case of vector, you just sum the couplings. The case of scalar, there are these effects. There is a running, of course, and yeah, there is a running here inside here. I'm not going through the full explanation. You can go to the Marco Cirelli paper to see how you can get this to have a coupling with the whole nucleon. Because you're looking at nucleons inside a coherent nucleus. That can be maybe confusing, but yeah, it's coherent nucleus, but you're computing for every nucleon. I don't know if that answers your question,
Yes.
Nicolas. Yes?
Yeah, perfect. Thank you.
Oh, thank you.
Very good. Roberto, have you got any questions? Do you want to go already to KM3 net?
No, I have a short question because it's kind of off topic. I mean, it's with the topic, but could be off topic, according with Jaime told us in the webinar. Yeah, I am wondering because sometimes when people, when you were mentioning the capture rate, and some people consider annihilation of dark matter within the compact object, or for instance in the sun. Let's go for the case of the sun. They used to analyze these cases or models that are called secluded, in the sense that it happens the annihilation within the compact object, and then the mediator can escape from the star and then decay outside the star. But if we wrap it up opposite, let's say that the dark matter could interact using this kind of mediator, it could be kind of a long range interaction between the dark matter flux with the compact object, let's say, because now the mediator can travel longer distance, let's say, because the interaction is with
I personally haven't seen models in which the mediator escape. Usually neutrinos escape. Higgsino's maybe can escape. I haven't worked on Higgsino, so I don't have much information about that. But no, they don't consider long range. Long range is always problematic, dangerous, and hard to account for.
Yeah, exactly.
So, yeah.
Because
Usually neutrinos.
No, yeah. I just
Yeah.
wondered about that because they were kind of popular, these kind of secluded scenarios because of with Ice Cube or with time Antares could measure the hypothetical flux of neutrinos from the sun coming from the annihilation within the sun itself. Yeah.
Yeah, of course. That could happen. So you can have annihilations, short range interactions, and then the neutrino escapes.
Mhm.
So you change the flux. You could also have on Earth, actually. Earth can capture dark matter, and then your geoneutrino flux changes. Yes.
Okay. Thank you.
Thank you for the question, Roberto.
All right, I think we do not have any more time. Jonathan Viñate was saying thanks. And then he made a couple more comments, but we don't have time, unfortunately.
Okay.
So to all viewers, before we log off, let me remind all viewers that next week we are celebrating our 10 years of organizing these webinars. Yes, 10 years. So we have a special event. We have, if everything goes according to plan, we'll have Rogerio Rosenfeld, Marta Lozada, Fernando Quevedo, and Diego Restrepo joining us. And also go through a bit of the history of law physics, I guess. Note that it's a different day. It will be on a Friday instead of a Wednesday, but that's it. All right, so thank you so much, Jaime, for this fantastic webinar, and we'll see you around.
Yes, thank you. Thank you for the invitation. I'm very happy to take part in this webinar and hope to see you all soon.
Great. Take care, everybody.
Take care. Bye-bye.